All right, in this test, we're going to be doing a t-test, or sometimes it's called the student's t-test. And it was basically invented to help us determine if there's a significant difference between two groups. So you can see in group number one, I have my period one midterm scores. And in period two, or column C, I have my period two midterm scores. So with all of this data, I think it is, no, it's not organized. So we might want to just quick organize it. So I'm going to highlight the data under tools or data. Yeah, under the data menu, I'm going to do sort range, column B, A to Z. And then I'm also going to sort column C. So data, sort range, column C, A to Z. So with looking at all this data, I could see the lowest scores were in the 50s and the highest scores were in the upper 90s. So some students really did well on this midterm. But just looking at the data, I can't tell if there's a difference between these two groups. So we're going to do some statistical calculations. We're going to do the average. So equals AVER AGE. What average would I like? Well, I'm going to highlight this data from B2. I'm actually going to go all the way down to B22, and I'll show you why in a second. So even if I highlight extra cells, as long as they're empty, that's not going to change anything. I'm not sure what this autofill is. Okay, so now I have an average of 75.25%. I'm going to leave both decimal places here because up above, all of my measurements have two decimal places. So at this point, I'm going to leave my two decimal places. Now the question is, why did I highlight some extra cells? Well, I knew that my next data set was also going to go from row 2 down to row 22. So now I could copy Command C, Command V, but the nice thing is if you just grab that little blue box in the lower right hand corner of your calculation, you can drag that over. It's still a good idea to double check that's doing the average from C2. You can click on the box and it'll highlight the data for you. So sure enough, C2 to C22 is exactly what we want. You could copy and paste the equation down below, and then you can simply say, okay, I don't want average, I want STDV. But notice how the problem up here is it's because we shifted down a cell. It's a smart formula. It shifted from B2 to B3. So I'm going to turn that back to B2 and B22. Now, if you remember from the previous video, the IQR test, because this is a smart formula, had we put a $sign in front of the 2 and a $sign in front of the 22, if I had copied and pasted my data down below here, and then I had typed STDEV, notice how the formulas have not changed. It's still B2 to B22. Done. Done. And now what I'll do is I'll drag my formula over to column C, and it's measuring from C2 to C22. Now, if you remember from the last video, one of the rules with standard deviation is we're only allowed to keep one, maybe two sig figs. So what we're saying here is we just have way too many decimal places. So we're going to go up to the decimal decrease button, and I can't go less than 0 decimal places, so I'm just going to keep it here at the nearest whole number. Technically, you could report this as plus or minus 10%. Without that 0 counting as a sig fig, but I'm just going to leave it to the nearest whole number here. One thing we didn't talk about in the last video is, now that we're rounded to the proper number of sig figs here, your average answer has to also match this level of certainty. So because my standard deviation is rounded to the nearest whole number, basically all of these decimal places are meaningless. So I'm going to round off my average to the same number of decimal places. So now I would report this as 75% plus or minus 11% and 80% plus or minus 11%. Now, as a teacher, one of the questions we often want to ask ourselves is, did period 2 score better than period 1? Maybe just from looking at kind of the hard work and the homework completion, maybe I'm thinking period 2 is probably going to score better on the midterm than period 1. So that's the statistical test we're going to calculate right now. So my hypothesis is I think period 2 scored better than period 1. Now the problem is, in statistics, we can't actually statistically support what we are trying to prove. We actually have to take a look at what's called the null hypothesis. So my hypothesis is I think period 2 did better than period 1. And some middle school students might actually make that claim because they're saying, oh, I think 80% is bigger than 75. But we can't do that. So what we're going to do is we're going to try to basically prove the opposite. So you might think the opposite of 80% is bigger than 75 is that 80 is less than 75. What we're simply going to do is we're going to say that these two groups were the same. The average for period 2 and the average for period 1 were identical, statistically speaking. So that's my null hypothesis. And if for some reason I can statistically disprove my null hypothesis, then that allows me to make the claim that actually period 2 did better than period 1. So it's a little bit weird in statistics. As far as this hypothesis testing goes, we don't actually support what we're trying to prove. We analyze the opposite, which is called the null hypothesis. So now I'm going to come up with my t-test. You'll notice that I linked these two cells together. So I did that by using this merge feature up here. So right now I unmerged them. There is only one value for the t-test. It's not like we're going to get one value for column 1 and one value for column 2. So I'm going to merge these back together by pressing the merge button. And now I'm going to type equals t-e-s-t, and sure enough it says, oh, you're calculating a t-test. It says, what's your first set of data? Well, my first set of data goes from B2 to B20. You could highlight the extra cells if you want. I'll do comma. All right, what's range number 2? Range number 2 goes from C2 down to C22, comma. The number of tails. So because I'm trying to prove that one group did better than another group, I'm only going to look at one end of a bell curve. In the last video, when we were talking about standard deviation, we went over a bell curve. So when you're looking at a group did worse than another group or a group did better than another group, you're going to focus on one of the tails. So as far as number of tails, I'm going to click number 1. Now, if my hypothesis is that I think period 2 was different than period 1, we're not saying whether period 2 is better or worse than period 1. I just think period 2 was different than period 1. And that's when you would use two tails. And then as far as my type, you can click the little type here. It tells you what type 1, 2, and 3 is. I think I'm going to have to zoom out a little bit here. I'm missing some of my... I can't scroll down anymore, but you can click on this and it'll tell you what the type is. We're going to do an unpaired t-test. So I'm going to click the number 2 because it says 2. Now what that means is, I'm going to hit enter. What that means is this score in row 2 has nothing to do with row 2, column C. It's not like this student was the same student as this student. When you would use a paired t-test is when you're looking at midterm scores versus final exam scores. So in this case, this would be student 2's midterm score, and this would be period student 2's final exam score. And I think that comes into play when we're looking at your second example problem or your second practice problem. That is actually telling you to do a paired t-test because this score is related to that score. But back in my example, just to review one more time, I highlighted the two sets of data. I'm doing a one-tailed t-test because I'm looking at better than, or in the opposite case, worse than. And I'm looking at type 2. Now I get a p-value. My p-value is 0.10. which basically means 10%. You'll notice over here it says that I have an alpha level of 0.05 or 5%. That's usually pretty good for like a high school science fair project. In the medical field, we would not be willing to live with like a 5% mistake. You might have to go with like a 0.01 or a 0.001. So what this is basically saying is I'm willing to live with a 5% risk of saying that the two groups are equal when they're not actually equal. Or I'm willing to live with a 5% risk of getting rid of my null hypothesis that the two groups are equal when I really shouldn't be doing that. And the problem is my data set came in at 0.10 or 10%. So if my cutoff is 5%, but there's a 10% chance that these two groups are actually different, then I'm not allowed to get rid of that null hypothesis. So the way I learned it, the little mnemonic device that I learned, is if this p-value is lower than 0.05, then the null hypothesis must go. So in this case, I'm not able to get rid of the null hypothesis, so I'm not able to say that 80% is better than 75%. And one reason is, if you look at these standard deviations, it's 11%. This number is not the number 80, it's 80 plus or minus 11. So people did all the way down from a 69 up to a 91, and this group did the average, kind of the bulk of the class went from a 64 up to an 86. So when you take a look at both bell curves, a lot of the data is overlapping in the middle. And again, we're not able to say that 80% was better than 75%. So again, it's this probability or p-value that says if we're allowed to get rid of the null hypothesis. And because this is a 10% error or mistake, and I'm only willing to live with a 5% error mistake, I have to keep my null hypothesis. I have to say these two groups are the same. So in practice problem number 1, you're going to do very similar to what I just did. And then in practice problem number 2, again, the only difference is that it's going to be a number 1 paired t-test. Because you want to see, did students do better on the final exam than they did on the midterm score? All right, that wraps up video number 2. In the next video, we'll take a look at the ANOVA test.